Hello, this is the Unit 1 Module 3 video office hour. We're going to go over questions that were covered during the week as we led up to the exam. This is from the practice exam that's under Exam 1 Content in our D2L page. So we have a mixture here of propane and butane and a little bit of nitrogen. These are the blue spheres. That's not stated, but there is a little bit of nitrogen there. And so as we go to analyze this problem, all right, we notice in terms of phases that there's a liquid phase and a gas phase. The liquid phase is a low potential energy phase, and the gas is a high potential energy phase. This is assigned based on average particle spacing. But since the tank is all at the same temperature, 15 degrees C, the average kinetic energy for both phases are going to be the same. Always the same if they're at the same average temperature. So we have a two-phase system, liquid and gas, three different substances. N2, the two blue spheres, C3H8 propane, and C4H10. Three different substances. How many chemical compounds are in the gas phase? Well, we only see one. Keep in mind that a compound has at least two elements that are different. We see two blue spheres, so the same element, so that's not a compound, but C3H8 is a compound because it's made up of carbon and hydrogen atoms. All right, how many elementary substances are in the liquid phase? Well, that's just going to be nitrogen. We do see one nitrogen particle in the liquid phase, and elementary substance is one that has the same, is made up of all the same atoms. In which phase are particles moving at a higher speed? Well, that would be gas, because it is the lightest of all three particles. So let's confirm that. So nitrogen is 14 grams per mole, and there's two nitrogens per particle, which gives us 28 grams per mole. C3H8 is 3 carbons at 12 grams per mole per carbon, plus 8 hydrogen atoms, each at a gram per mole each, and we add that up, we get 36 plus 8 for a total of 44 grams per mole. And for C4H10, we take 4 times 12 grams per mole plus 10 at 1 gram per mole, add these together, and we get 58 grams per mole. So we see that if we have the same number of particles, which is 1 mole, nitrogen would have the lowest weight of 28, or lowest mass, and C4H10 would have the highest mass. That is why C4H10, being the heaviest, would move slower, and nitrogen, being the lightest, would move the fastest. In which phase do particles have the lowest potential energy? In this problem would be the liquid. Liquid particles are much closer together in the gas, so they would have the lowest potential energy. In which phase do particles have the highest kinetic energy? Well, they would be the same, right? All phases have the same average kinetic energy because it's the same in both. How many different substances would we have in the system if all of the liquid propane gas is boiled and transformed into vapor? That would be 3. We'd have N nitrogen, N2, the blue spheres, the C3H8, and the C4H10. Each of these would remain intact, the particles. They would just transform from liquid phase to gas phase. All right, so we had this question from the practice exam. So again, we see two phases here, liquid and gas. Liquid is the lower potential energy due to particle spacing. and gases would have the higher potential energy because they're farther apart. If we drew a Peck diagram based on the data that we see here, we'd first draw a vapor pressure curve looking at the data. And so we see that nitrogen, all of nitrogen is in the gas phase, so that would probably have the lowest boiling point, or the line that's farthest to the left. There's one C2Cl4 that is in the gas phase, so we would consider that to be the next highest boiling point. And then all the water particles are in the liquid phase, so that would be the highest boiling point. So if we had to register these three substances as pressure and temperature here, we would say nitrogen would have the lowest boiling point, H2O would have the highest boiling point, and then C2Cl4 would have the intermediate boiling point. So that's the lowest, next highest, and then water would be the highest. So that gives us some insight into the potential energy of the liquids, which we're going to use to construct the Peck diagram. So here we have a Peck diagram. We're going to put gases in the top right. They have highest potential energy and highest number of configurations because there's no restriction on their movement. All the gases are pretty much together at high potential energy, same number of configurations. It's the liquids that have different potential energies because they have different boiling points. So as the boiling points increase, we move down in potential energy. So nitrogen is the highest or least stable liquid, the weakest interaction, C2Cl4. And then we expect water to have the highest boiling point. Right, water would have the highest boiling point because no particles are found in the gas phase. So lowest boiling is always at the top of the potential energy for the liquids. Highest boiling point is always at the bottom. Has the strongest interactions, lowest potential energy. Lowest boiling point would have the weakest interactions. And so in the question that asks for the phase that has the lowest potential energy, well, we would pick liquid. But all of this are types of questions that we covered in the office hours. So this is how you can construct a vapor pressure curve and a Peck diagram from the information given. Okay, so here we have the same type of information. Instead of at the submicroscopic level, we're given just boiling points. So with this information, we can construct a vapor pressure curve for three different substances. Remember, this is the liquid-gas interface. So, Okay, so we go through pressure and temperature. We put the highest boiling point to the far right, lowest boiling point to the far left. And so the substances that's most volatile is CH4, has the lowest boiling temperature, and requires the least amount of energy to separate the liquid particles. The substance have the strongest attractive interactions or strongest intermolecular forces. That's going to be propane. That's because propane has the highest boiling temperature, meaning it requires the most kinetic energy to separate or overcome the liquid attractive interactions. This is also called intermolecular forces. So attractive forces or intermolecular forces, whatever requires the highest temperature to boil will always have the strongest interactions. Whichever has the lowest boiling point will have the weakest. And then which subparticles do have the lowest or the higher potential energy? So now we make the Peck diagram. Here's our gases again in the top right. They're all pretty much the same potential energy, same configurations. It's the liquid potential energies that give us our boiling points, and so methane must be the highest potential energy because it's got the lowest boiling point. And then the propane has to be the lowest potential energy, has the highest boiling point. So the highest potential energy, most unstable liquid must be CH4 since it has the lowest boiling point. Okay, so we're going to do some calculations. Here's one that was asked from the exam. We can see that we can see that first the liters don't really matter, so we just want to know how many particles are there in our molecules in 0.023 grams of CH4. Sorry. So as we go through this, what we're saying is we want to go from grams of CH4 to moles of CH4 to particles of CH4. Okay, so that's the general plan of what we want to calculate. We always go from the given information, which is grams. We always have to convert to moles or find out, do we have a mole? And then we'll know how many particles we have. So we just ask ourselves, well, what is a mole of CH4? So we add up, it's 12 grams per mole, because there's 1 carbon, plus 4 hydrogens at 1 gram per mole. We add that up, and we get 16. So if we had 16 grams of CH4, then we'd have 1 mole of CH4 and 6.02 times 10 to the 23 particles of CH4. So that would be a really straightforward problem. If we had 16 grams, then we'd have 1 mole, and we'd have Avogadro's number of particles. But we don't have 16 grams. We only have 0.023 grams. So we need to know what fraction of a mole is 0.023 grams. So we take 0.023 grams and we divide it by 16 grams per mole. Right? That'll give us the fraction of a mole. Because we don't have 16 grams, which would be exactly a mole, we have some fraction of it. What's the fraction? Well, it looks like we only have 1.4 times 10 to the minus 3 moles. And if we only have that number of moles, when we multiply by Avogadro's number, we'll see that instead of having Avogadro's number of particles, we have 8.6 times 10 to the 20 molecules of CH4. So this is a really useful way to do the problems, is that you think about the problem and say, well, if I had the molecular mass, if I had 16 grams, I'd have 1 mole and 6.02 times 10 to the 23rd. But if you don't have exactly that mass, then you would just take whatever you do have, divide it by the molar mass, and then multiply by Avogadro's number. Okay, so here's a question from the homework. And so we had a lot of questions in the office hour about it, so let's go through it. So this might be one of, your question might not be exactly the same, but it's more or less the same way to do it. So the question asks, you have a density of 1.53 grams per meters cubed, which is a volume, and they want to know how many molecules there are in 2 liters. And then they give us a conversion of meters cubed into liters. Say, okay, great. Well, it would have been nice to have had the grams per liter to begin with. But so let's calculate it. So if we have 1.53 grams per meters cubed, then what we would do is multiply by the conversion factor that they gave us. So the 1 meters cubed divided by 1,000 liters. If we do that, we get the 1.53 grams per liter, and it also has times 10 to the minus 3 because we're dividing by 1,000. And then it says we don't have just 1 liter, we have 2 liters. So then if we multiply by 2 liters, then in the end we get the total number of grams is 3.06 times 10 to the minus 3 grams. So the first thing we do is we convert to grams per liter and then multiply by how many liters we have. So we only have 1 liter, then it's 1.53 grams times 1.53 times 10 to the minus 3. If we have 2 liters, we have 3.06 times 10 to the minus 3. So now we can do the problem. So we have 3.06 times 10 to the minus 3 grams of CClF3. Okay, so we go through this, and now what we want to do is CClF3. And so we sort of just do the same methodology as the previous problem, which is how many grams are there in 1 mole of CClF3? Well, we take 12 grams per mole for carbon, 35 grams per mole for chlorine, 19 grams for fluorine, but we have 3 of them, so we multiply by 3, and you add those up, and we get 104 grams for CCl3. So this tells us that if we had 104 grams of CClF3, we'd have 1 mole of ClF3, which would be 6.02 times 10 to the 23rd particles. But we don't have 104 grams. We only have a fraction of that. So we take how much we have, 3.06 times 10 to the minus 3 grams, and then we divide it by our molar mass. That gives us how many moles? 2.9 times 10 to the minus 5 moles of ClF3. Then we have that fraction, we take that number, multiply by Avogadro's number, and then we get the number of particles, 1.7 times 10 to the 19 molecules of CClF3 in 3.06 times 10 to the minus 3 grams. So same methodology. The first thing you need is the mass. You ask yourself, do I have the mass that's exactly equal to 1 mole? And if you don't, then you divide by that mass. That's exactly 1 mole. And then multiply by Avogadro's number. Okay. So now the question is, now we're given the number of moles, we want to know how many grams of CCl3F that corresponds to. Okay, so we first find out, well, how many grams are in 1 mole of CCl3F? So we add this, it's 12 plus 3 times 35, 3 chlorines plus 1 fluorine. We add this up, and we get 136 grams per mole. So if we had 1 mole, then we'd have 136 grams. But we don't have 1 mole, we have 9. So we have to multiply the 9 moles times 136 grams per mole. If you multiply those together, you get the total amount of grams as 1,224 grams of CCl3F. If we put that in scientific notation, it's 1.2 times 10 to the 3 grams, and that would be answer C for us. All right, so this was on the activity in the Wednesday class, so let's take a look at this. So we have a formula for a particle that's C4H10. So the question asks you to select all the correct answers. So let's take a look. So each particle has 4 carbons and 10 hydrogens. Another particle, 4 carbons, 10 hydrogens. Another particle, 4 carbons, 10 hydrogens. So we see that the first answer is definitely true. Every particle has 4 carbon atoms. Every particle has 10 hydrogen atoms. Every particle has 4 plus 10, which is 14 atoms. So that's true. So we definitely have the first 3 true, because at the particle level we would definitely have 4 carbons, 10 hydrogens, and 14 in total. Now the question is, do all the particles of this substance have the same formula? And the answer is yes, because that's what makes it that substance. If we had something that was 3 carbons and 10 hydrogens, well, that wouldn't be that substance. It'd be something else. So just keep that in mind. All the particles of the same substance will have the same formula. So all the answers are true for this problem. All right, and so for this problem, the last one of the video, is we're given some data about nitrogen, oxygen, helium, and hydrogen. And then we're asked to find out which substance has the lowest potential energy in the liquid. So it really helps to draw a vapor pressure curve just to get an idea in terms of potential energy. This will help us organize our thoughts. So if we were looking at the different boiling points, we'd see that one of them is definitely the lowest temperature boiling, that's minus 268. That would be helium. Then there would be hydrogen at minus 252. Then there would be nitrogen at minus 195. And the highest boiler would be minus 183, which would be oxygen. That means if we were going to write out the Peck diagram for this, we would have all the gases together, right? They all have the same potential energy. They're pretty much near zero. High potential energy, high configurations. And then we would have to place the four liquids. So we would put the lowest boiler, right? So the lowest boiler would be helium and then hydrogen. So I would switch that. Nitrogen and then oxygen. So we'd have the lowest boiling point would have the weakest interactions. Highest boiling point would have the strongest interaction. That would be O2. So the question is, which of these would have the lowest potential energy, the strongest molecular forces? Well, that's the one with the highest boiling point. Highest boiling point here is definitely going to be oxygen, right? Oxygen has the lowest boiling point. The highest boiling point of minus 183 C. The one with the highest potential energy and weakest intermolecular forces would be helium. So that would be helium, not hydrogen. There you got switched here, but helium would have the lowest boiling point, so it's definitely going to have the highest potential energy and the weakest intermolecular forces. All right, so that's the Unit 1, Module 3 video office hours. I hope that helps with the questions that you'll be asked on the test and also on the homework.